Good morning, young physicists. Let me ask you this: why do we build bridges with steel and not with rubber bands? The secret lies in something we call the elastic modulus, a fancy name for how stiff or flexible a material is. When you apply stress, which is force per unit area, a material undergoes strain, which is the fractional change in length. Now, within the elastic limit, the ratio is constant. That ratio is the modulus of elasticity. Big modulus. The material resists deformation like a stubborn mule. Small modulus. The material bends and stretches easily. Simple, right? Let's start with the most famous one, Young's modulus. It's defined for tensile or compressive situations. Mathematically, Y equals stress divided by strain. Now recall, stress is F over A and strain is delta L over L. Substituting, we get Y equals F times L divided by A times delta L. That means if you pull a steel wire, the extension delta L depends on the applied force, its original length, and its cross-sectional area. Metals like steel and brass have very high Young's modulus, which is why they hardly stretch. Wood and concrete, on the other hand, have much smaller values, they yield more easily. Next, imagine sliding the top of a block sideways while keeping the bottom fixed. This gives us shear stress and shear strain. The ratio of these two gives the shear modulus G. Formula: G equals shear stress over shear strain. If the strain is measured as an angular deformation theta, G becomes force divided by area into theta. In simpler words, shear modulus tells us how resistant a material is to being twisted or sheared. Steel has a high value, so it's rigid, while wood is much lower and hence more flexible. As the diagram shows, the slab deforms into a parallelogram when tangential force is applied. Now think of squeezing a rubber ball equally from all sides. The ball shrinks in volume but keeps its shape. This is where bulk modulus B comes in. Definition: bulk modulus equals stress over volumetric strain. Stress here is pressure, the same from all sides. Volumetric strain is change in volume over original volume. The formula is B equals minus P divided by delta V over V. The minus sign reminds us that when pressure increases, volume decreases. The reciprocal of bulk modulus is called compressibility, a measure of how easily something gets squeezed. Solids like steel are very incompressible, while gases are ridiculously compressible, almost 1,000,000 times more than solids. Let's check out some real numbers from the tables. Young's modulus, steel, around 2 × 10 to the power 11 pascals. Concrete, just 3 × 10 to the power 10 pascals. That's why steel is preferred for bridges, while concrete alone can't handle much tension. Shear modulus, steel again dominates at nearly 8 × 10 to the power 10 pascals. Wood is way lower. Bulk modulus, iron is about 1.6 × 10 to the power 11 pascals, but water is only 2.2 × 10 to the power 9. And air? Practically negligible, 10 to the minus 4. These numbers aren't just trivia. They decide whether a material becomes part of a skyscraper, a cushion, or even a balloon. Time for some problem solving. Example: a steel rod of radius 1 cm and length 1 meter is stretched with a force of 100 kilonewtons. Young's modulus is 2 × 10 to the power 11 pascals. Find the stress, elongation, and strain. Step 1. Stress equals force divided by area. That's 100,000 divided by pi into 0.01 squared. Result: 3.18 × 10 to the power 8 pascals. Step 2. Elongation delta L equals F times L divided by A times Y. Substituting values, we get 1.59 into 10 to the minus 3 meters or 1.59 millimeters. Step 3. Strain equals delta L over L, that's 1.59 times 10 to the minus 3. Dimensionless as expected. So, the rod experienced a huge stress, a tiny elongation, and a very small strain. This shows how resistant steel really is. But wait, when we stretch a wire, where does all that work go? Into the gym? No, it gets stored as elastic potential energy. For a wire stretched by delta L, the work done is half into Young's modulus into strain squared into volume. Another way to say it, energy per unit volume equals half sigma into epsilon. This is beautifully shown by the area under the stress-strain curve. That area is not just geometry, it's stored energy that can be released if the stress is removed. This principle powers springs, suspension bridges, and even the strings of a guitar. Let's tie all this together. Elastic modulus is stress divided by strain, a measure of stiffness. Young's modulus tells us resistance to stretching or compression. Shear modulus deals with shape changes. Bulk modulus explains volume change under pressure. Elastic potential energy is stored in a strained wire. And the values of these moduli decide what materials we use for buildings, machines, or everyday objects. So the next time you bounce on a trampoline, bend a scale, or even sip through a straw, remember, elastic moduli are silently at work. That's it for today's concept. I hope the stiffness, squishiness, and stretchiness of materials now make complete sense. See you next time with another fascinating physics journey.